Hello everyone, my name is Charles Bonnineau and I will present you my research paper called Multitask Learning for VVC Quality Enhancement and Super Resolution. This research work was selected as an oral presentation for the conference PCS 2021 and was conducted with the support of Wassim Amidouche, Jean-François Travers, Nati Sidati and Olivier Desforges.
In July 2020, a new video coding standard called Versatile Video Coding was released. This compression standard offers around 40% of bitrate reduction over its predecessor HEVC, answering to the high bandwidth requirements of new video formats like 8K, HDR, or HFR, developed to improve the quality of experience of the end users. In parallel, learning-based post-processing algorithms have been investigated to improve the video coding efficiency. These learning-based approaches are based on convolutional neural networks and have outperformed more traditional solutions like interpolation or filtering methods. For example, super resolution can be used in a coding pipeline to recover high-resolution details from low-resolution compressed videos. Indeed, some works propose to use it in a static or a dynamic spatial resolution adaptive scheme to improve the coding efficiency at low bitrate. It also offers a kind of spatial scalability as different resolutions are available at the decoder side. On the other hand, quality enhancement without upscaling can be used to remove the coding artifacts generated during compression. This kind of module can be used as a standalone post-processing step or integrated directly in the coding loop as in loop filter. However, all these learned approaches require many parameters to be efficient, making them very hard to deploy in real-world use cases. Let's have a look on this quick example. Here, given an input image ILR, we want to encode it with VVC using a given quantization parameter and decode it to obtain the reconstructed degraded image. As discussed just before, we may want to apply some post-processing using dedicated CNN models to restore the decoded image. For example, here, super resolution can be applied for upscaling using a first dedicated model, or quality enhancement can be performed to remove the coding artifacts generated at a given QP using another dedicated model, or using another network optimized for another level of degradation, and so on. Here, we clearly see that all those learned models may contain redundant features that are not exploited. This is the reason why, in this work, we propose to use multitask learning to exploit this redundancy using a single shard network and two task-specific submodules, one for super resolution and one for quality enhancement. The low-resolution decoded image is given as input to our network with a QP map that indicates the level of degradation introduced during compression. Those inputs are passed through the shared CNN and splitted towards both task-specific submodules to reconstruct the two different reconstructions. Here are presented the details of our proposed architecture. Our model is mainly based on EDSR, that is one of the state-of-the-art models for super resolution. This convolutional neural networks uses a residual architecture with long and short skip connections that make easier the training of very deep networks. We adjust the number of parameters by varying the number of residual blocks denoted by the letter B here. For multitask learning, we simply propose to use hard parameter sharing and perform the task-specific split at the very end of the network. This allows us to maximize the sharing between the tasks and maximize the sharing of parameters as feature maps are computed once. Also, to allow a single model to be trained for multiple levels of degradation with a limited impact on the performance, we also use a QP as input to the network, represented by a 2D normalized map called QP map. To train such a multitask network, we need to compute a multitask loss. In this work, we simply combine both task-specific losses computed using the L1 loss by a weighted sum using a parameter alpha. We set empirically alpha to 0.9 after a grid search on different values from 0 to 1. Regarding the optimization parameters, we use the learning rate of 10 to the minus 4, a batch size of 8 on the optimizer Adam. To initialize the weight of our networks, We first pre-train it for super resolution on uncompressed images as our network is mainly based on EDSR. Now regarding the dataset, for training, we use 48 by 48 pages extracted from the well-known Dive2K image dataset that contains thousands of high-resolution images. As a validation set, we use a set5 dataset, and for testing our method, we use the GVET CTC video sequences encoded in all-in-track configuration. For data generation, we first apply a bicubic downscale on the high-resolution images and apply compression by using the VTM, that is the reference software of VVC, in all-in-track configuration for the different values of QP from 22 to 37. Let's have a look now on the results. Here are the results of the first ablation study. We wanted to evaluate the impact of the different elements of our architecture for both tasks and for different values of QP. This experiment has also the objective to clarify the impact of training separate networks for different QP versus multi-QP optimization strategy. Here, the performance is assessed using the PSNR, and cross markers correspond to the full configuration without the corresponding element. We clearly see that fine-tuning improves the performance of both tasks, although it was pre-trained for super resolution. It shows that features learned for super resolution are powerful low-level vision features that can be exploited by other tasks. We also observe here that QP maps allows to improve the performance of both tasks for multi-QP training strategy. It makes it comparable with multiple networks trained for different QPs. For the multitask learning evaluation, we compare our approach with single-task networks trained for each task. We also include a sequential configuration for super resolution, here in orange, where quality enhancement is applied before super resolution processing. If we look at the red and green bars, we observe that for the same number of parameters, our approach proposes similar performance than two task-specific networks while allowing both tasks to be performed. Moreover, for the same total number of parameters, and in a context where both tasks have to be performed, see here the red and blue bars, our multitask model proposes gain over single task networks. And finally, for super resolution, the sequential processing of quality enhancement and super resolution proposes lower performance than using a deeper super resolution model or our multitask approach. All these observations can be explained because the redundant features that are computed twice between the dedicated models are mutualized using our approach. Let's have a look now on this quick simulation. Here, we visualize two single task networks, one for quality enhancement and one for super resolution. If we look at the learned features and make them match each other, we observe that an obvious similarity between the features. The same observation can be made for a deeper layer. As explained before, our approach proposes gain in quality compared to single task networks if both tasks have to be performed and considering the same total number of parameters. Here, we evaluate this observation on the GVET CTC sequences. And here, our model offers around 2.8% of bitrate reduction for the same PSNR score regarding super resolution and 2.34% regarding quality enhancement. Now, to conclude, in this paper, we studied a CNN-based multitask approach for post-processing. We have demonstrated that learned features can be mutualized between different tasks to reduce the number of stored parameters. We also studied a training strategy based on fine-tuning on the use of prior information to train one network for multiple levels of degradation. To summarize, our approach proposed to perform two tasks and is optimized for multiple levels of degradation using a single shared network with no impact on the performance. As future works, we plan to extend this model for random access configuration by exploiting the temporal component. Thank you everyone for your attention, and I'll be pleased to answer your question during the dedicated session.